Hello and welcome. What we're taking a look at here are irrational and complex conjugates. And first of all, what is the distinction between the two? What does each of those mean? And then what is it that it allows us to say? Well, first of all, irrational conjugates are values, zeros, that are made up of a real part and a second real part, but one is rational and one is irrational. So irrational, for example, would be a square root of 2, would be an irrational number. A complex conjugate would start off with a zero that is complex. So you have a real part and an imaginary part. Our part that includes that letter I, which stands for the square root of -1. So the irrational conjugates theorem says let f be a polynomial function with rational coefficients, and let a and b be rational numbers such that b has a square root that is irrational. So for example, 1/2 is an irrational square root, or will have an irrational square root, and something like 1/4 does not, because the square root of 1/4 is itself 1/2, and we would just write it as 1/2 in that case. So in this setup, if you have a plus the square root of b, so that's that rational and irrational pair of parts, if that's a zero, then a minus the square root of b, where you change the sign on the irrational part, is also a zero of your function. Kind of in a similar vein, but notice there are some differences. Let f be a polynomial function with real coefficients. Notice there's a slightly more relaxed condition there. It doesn't have to be rational, just anything that's real. And let's assume that a plus bi is an imaginary zero of f. It has that real part a and that imaginary part b. If b were to equal 0, we would consider this only real, and we would not say that it applies here. Well, if that's true, then a minus bi, so again, switch that sign, but this time on the imaginary part, is also 0 of our function f. And so how do we use these? What do they let us say? So the big one is kind of the obvious one. It's a 2-for-1. If you know one of the zeros, you know a second. So the moment someone tells you one imaginary zero or one irrational zero that fits this description, then you have a second one that you already know. And what that allows us to do then is, secondly, it allows us to create quadratic factors. If you take the zeros, the conjugate pair of zeros, and you turn them into their corresponding factors, well, you can multiply those together, and you have two linear factors multiplying, it'll give you a quadratic. And it turns out that because of how you set those up, it'll give you a very nice, neat, rational coefficient quadratic. It'll actually give you something that's very straightforward to work with, at least in the cases that we'll be interested in. Now, it is worth noting that in the case of this irrational conjugates theorem, we have a very specific setup, and it's easy to miss this sometimes. So let me give you an example. Is a plus pi is an irrational number, going to fit this description? And the short answer is no. Pi is not the square root of a rational number. Pi is just pi. It's just kind of a random assortment of never-ending numbers that has no distinct pattern. So there's actually a lot of numbers like that, way more than we have specifically named or listed. So yes, this works nicely with roots of rational numbers, but there are a ridiculous number of irrationals for which this would not work, and you can actually find something like, say, a third-degree cubic function that has 3 irrational zeros. They don't have to come in pairs in that sense. So instead, this specifically works with square roots of rational numbers. So what's an example of this? Well, let's say we have 2 plus the square root of 3 as a zero of our polynomial. What's another zero of our polynomial? Well, 2 minus the square root of 3. We take that square root of 3 and we switch the sign. Note that if we wrote this as the square root of 3 plus 2, we would still change the sign on the irrational portion. So it would become negative square root of 3 plus 2. So you have to be very careful that you're always either writing it in that a plus root b format, or you're always remembering that it's the irrational number that's changing sign. You can, in theory, multiply things together by changing the a value sign, but it will not be what we consider the conjugate of the zero. Similarly, with the complex conjugate, what if we have 2 minus 3i as a zero to some polynomial? Well, what's the other zero that we can say? Well, it's 2 plus 3i. Again, you switch the sign on the imaginary part. Now, as a quick note, what's the relationship between a zero and a factor again, just to remind us? Well, the zero is the value. It's the x value, typically. while the factor is an expression. So it's usually x minus that value. Or if we distribute the subtraction, in the case of our example, 2 minus 3i, we have x minus 2 plus 3i, because the subtraction distributes to the negative 3i and makes it a plus. What's the corresponding factor for the 0 to plus 3i? Well, that's going to be x minus 2 minus 3i. Again, make sure you remember to distribute that subtraction. Okay, so what can we do with these conjugate factors? Well, we can multiply them together. And so if you actually take a look at this, there's actually a very nice little setup that exists for conjugates. You always have x minus, and the first number, the a value, is always the same. So you'll notice both of these have an x minus 2. And you'll also notice that the last term is always the same because it's just the same thing but with a different sign, which means we actually have a setup very similar. In fact, it is a difference of squares. A plus b times a minus b. And so we can actually take advantage of that because the difference of squares, when we're multiplying them, says we have a squared minus b squared. Well, if a is x minus 2 and b is 3i, we get x minus 2 squared minus 3i squared. Well, x minus 2 squared is x squared minus 4x plus 4, and 3i squared is negative 9. So we have minus negative 9. Be sure you don't forget that that subtraction was there from the beginning, which is the same as a plus 13 at the end, so we get a plus 9 at the end, which gives us, in the end, x squared minus 4x plus 13. Now, very lastly, why conjugate pairs? Like, where do these things come from? Why do they exist in pairs at all? And the answer, actually, is something we've been working with for several years now. The quadratic formula. If you take something like the result we just got and you try to tear it apart, if you try to factor it, well, we learned that if it's not nicely factorable, which it's not, and it doesn't follow any neat factoring rule, which it doesn't, we basically are going to try and use the quadratic formula. So a is 1, b is negative 4, c is 13. And when you set this up, you are going to eventually get 4 plus or minus the square root of negative 36 over 2. Well, 4 over 2 is 2. The square root of negative 36, square root of 36 is 6, square root of negative 1 is I, so it's 6i over 2. And when you simplify that, you get either 2 plus 3i or 2 minus 3i, which are the two values you've got. The quadratic formula, because of the shape of parabolas for quadratic solutions, we have the exact same value, basically the axis of symmetry, plus a little more to one side or to the other. And that little more to the one side or the other is always the same because of the symmetry of parabolas, so we always get plus or minus the same value. That square root is what causes the imaginary number if it's a negative inside the square root. That square root is why our irrational conjugates theorem uses square roots specifically, because it all comes from the quadratic formula. I hope this helped you out, and see you next time.